The graphical user interfaces we interact with every day, the windows, the icons, the cursors, are computationally expensive illusions. They exist to make computing comfortable, but they mask the underlying text-based architecture that actually runs global infrastructure. True enterprise computing strips away that graphical layer entirely. It operates on headless systems controlled entirely through text. This text-first approach powers the massive web servers and data centers that host the internet. It runs the point-of-sale checkout registers you scan your groceries on. It dictates the logic for critical infrastructure, from automated traffic light networks to industrial sensor arrays. You will even find it embedded directly into the entertainment and control panels of modern vehicles. To understand how modern computing actually functions at scale, we have to look at the environment that powers all of these systems, the Linux terminal. Operating reliably across thousands of devices requires shedding the massive overhead of graphical interfaces in favor of pure textual efficiency. The architecture behind this efficiency dates back to 1991. A university student named Linus Torvalds wanted a free alternative to the complex and expensive operating systems of the time, like Unix. Working out of the University of Helsinki, he released the first iteration of his system to a public news group. What Torvalds actually built was the kernel, the core engine of an operating system that manages hardware and memory. Because this kernel was open source, developers could wrap it in different sets of tools and package it into distinct versions, known as distributions. Today, one of the most prominent, extensible distributions used for enterprise servers is Ubuntu. A standard graphical operating system devotes massive power just to render visuals. In contrast, a headless Linux server runs a minimal process tree. The resource gap is extreme. An entire Ubuntu server operates smoothly on just 512 megabytes of RAM. We intentionally trade visual comfort for computational efficiency. To harness that power, you have to master textual system primitives. When you connect to a headless system, your only viewport is the terminal prompt. This split screen shows how those text commands translate to spatial awareness. The left side is your interface, the right side maps the server's hidden file system. Without a graphical map, your first priority upon connecting is defining your starting context. Typing the command "Who am I" tells the system to return your current username and verify your active permission profile. Even with your identity confirmed, a headless environment is initially disorienting. You need spatial coordinates. The pwd, or print working directory command, calculates and outputs the absolute path of your exact location within the server, but you are still functionally blind. You cannot automatically see the files that exist in the directory around you. You execute the ls, or listing, command to map out the names of the files and folders occupying your immediate space. You can append arguments to this command, like typing ls pictures, to probe the contents of a distant folder without having to actually move there. When you do need to move, you use cd, change directory, to shift your working coordinates to a new location. Traversing the system only gets you to a file. Next, you must extract its data into your terminal display. The cat command, short for concatenate, dumps raw text from that target file directly onto your screen, allowing you to read exactly what is inside. By combining these short text strings, you completely replace the computer mouse, maintaining precise control over your spatial traversal and system state. Navigating manually with CD and ls is fine for a handful of folders. On an enterprise-scale server with thousands of nested directories, it becomes impossible. You have to evolve from manual movement to algorithmic data extraction. This animation shows the find command. Instead of walking through folders, you instruct the system to recursively sweep the entire file structure for a specific string of text. If you lack the exact file name, input an asterisk. This wildcard commands the algorithm to broadly look for files sharing a specific extension. Running a wildcard search for .text bypasses the folder structure entirely, simultaneously locating multiple targets across isolated system branches. Locating a file is one problem. Searching inside the raw data of those files is another. Take a web server's access log. Even a small one can contain hundreds of dense, unstructured entries. Dumping this entire file to your screen manually is highly inefficient if you only need to analyze a single metric.
Suppose we need to isolate the traffic generated by one specific IP address out of all this noise. This is where we apply grep. It is a pattern-matching algorithm that filters the text stream, illuminating only the specific lines containing the exact IP address we defined. By adding a recursive flag to the command, grep upgrades its search, sweeping through the contents of every single file in every subdirectory at exactly the same time. Search algorithms completely transform the terminal from a basic navigation interface into a highly precise, high-speed data filter. Individual commands are useful, but the true power of a Unix-based system lies in composability. You can chain isolated commands together to build complex, automated workflows. This schematic visualizes terminal commands as modular blocks. Shell operators are the physical routing junctions that control how data flows between them. Long-running processes normally freeze your terminal, but appending an ampersand pushes the process into the background, instantly freeing your prompt. Meanwhile, a double ampersand acts as a conditional gate, where the second command only executes if the first succeeds. Beyond controlling processes, you also dictate where the data actually goes by manipulating standard output, the stream of text normally forced directly to your display. For example, the simple echo command generates text and bounces it right back to your screen, but attaching a greater than operator redirects the output entirely. Instead of hitting your screen, the text is forced into a designated file. This specific operator is destructive, completely erasing any historical data in the target file. The double greater than operator is the safe alternative. It appends new output directly to the bottom of the file, safely stacking the new data without replacing the old. There are no graphical confirmation windows or heavy interfaces to slow these operations down. Shell operators take basic, lightweight system primitives and route them together, allowing you to architect automated, enterprise-grade data pipelines.